Welcome to Mars Robotics, place where we are going to build stuff that will teach us more about algorithms, statistics and problem solving. We embark on an ambitious mission to uncover secrets of Mars using rovers. Meet Ralph. This is his first mission and one of many crazy adventures that await him during his stay on Red Planet. Mars is one of our closest candidates to colonization and in many ways very similar to Earth. Well, maybe besides murderous dust storms, radiation, low temperature, and a general lack of oxygen. This presents interesting challenges, which we can try to overcome with simulations. As this is episode 1, it's worth to get to know Mars and Rover with his tools, which he will use during his journey across Mars. Let's take a closer look at available toolset. As you probably know, this is what the map of Mars looks like. For our purposes, we're going to simplify this comfy image into a hexagonal grid, that is, a big hexagon built of smaller hexagons. Here it's a map of size n = 5, because it has 5 hexagons per each flank. This allows us to perform more interesting maneuvers than those allowed by the grid found in a simple rectangular chessboard. Also, it has a pretty cool shape. Similarly, the rover presents us with equally sophisticated looks, considering its all advanced tech. We, however, are going to simplify this creature to a black dot on our hexagonal map. It's worth to mention that although we don't know the exact direction at which rover is looking, he remembers his orientation. Last but not least, let's define the goal, which Earth scientists strive for. It could be some ore, habitat, Martian phase, or even derelict ship. Whatever comes to our minds, we're going to represent it with a hex, in that case a green one. Before we set Ralph for an adventure, we need to equip him with tools that will help him reach the goal in a certain amount of time. Additionally, each action will cost him energy. He can drive forward and back, rotate by 60 degrees, scan surrounding area and recharge his batteries, which for now have a maximum capacity of 100. Let's see an example of how Ralph moves and how much energy he spends. For starters, he drives 3 fields forward, losing 12 units of energy. Next, he rotates by 60 degrees to the left, spending 2 units of energy. Then, he drives another 4 fields forward and loses additional 16 units of energy. Afterwards, he performs the scan, losing 15 units of energy, recognizes the target and turns left in exchange for additional 2. Lastly, he drives 1 field forward. In the end, he lost 51 units of his energy while working for 61 units of time. After that, he will report that he has successfully reached the target, to let the scientists wind down after they have waited so impatiently. After this short introduction, let's take a look at our problem, namely, how do we find ore, satisfy scientists and don't lose too much time on solving the issue. In this series, called Mission 1, we are going to explore different approaches, first of which is the random search. Random search is an example of a naive algorithm. The naive algorithm is the one that behaves in a simple manner, ineffectively, but getting the work done. We can compare it to a childlike approach, in a sense that although it has a simple structure, its effectiveness isn't particularly high, but it will get the job done sooner or later. Let's take a closer look at how random search is structured. Algorithm built in this way will make Ralph immediately scan a surrounding area, hoping to be lucky. It may happen he landed just next to the ore. Next, he will pick a random direction and drive 4 fields forward. Then, he will pick a random direction again and drive another 4 fields forward. Ralph does that in order to move away from the previously scanned area. He then scans the area with the radius of 2 fields and recharges his batteries. If Ralph found the ore, he will navigate to its exact location to then finish the mission. If the ore has not been found yet, he goes back to picking up a new direction and following the algorithm until reaching the target. What this all means is that ore can either be found very easily, just like this, or the quest to find it could last much longer. Let's examine some optimistic and pessimistic scenarios. In the case of an optimistic one, the whole search can end up nice and fast before you get a chance to say Mars. As we can see in the picture, just after the second scan, Ralph finds the goal and moves to its position. In a pessimistic case, Ralph can circle far away or even around and very close to the target and do it for a long time, which significantly prolongs the searching time. Scanned areas can overlap, so there is a risk of losing resources on scanning the same fields multiple times. That allows us to formulate the thesis that we can expect different execution times similar to the ones shown on this chart called a histogram. Histogram is one of the most popular statistical charts. It's used to describe frequencies of observations grouped in equal width intervals, often called bins. For example, the following histogram of IQ distribution allows us to conclude that the biggest group of people had IQ around 100. IQ equal to 60 and 140 is far less frequent, that's why bars are very low. We can make an assumption that the histogram of our rover is going to have similar distribution, with lots of average times and a few extreme ones. So now, after we've gone through the basics, let's dive into the fun part. For starters, let's analyze a simple map of size n equal 10, which has 271 hexes. That sets the effectiveness of Ralph's scanner at 7% per a single scan. Fields marked with blue dots represent already scanned areas. It makes observing rover in action much easier. Ralph has no scanning memory, so there is a risk that he's going to scan the same fields multiple times. Let's look at the first simulation in real time and see how he handles the problem on the map of size 10. As we see, his time effectiveness is far from optimal, yet sooner or later he finds the goal. Now let's look at his time efficiency after performing 1000 simulations to see average time and the histogram. Can you guess the shape of the curve and the average time needed to find the ore? Well, it turns out that after 1K simulations, Ralph may actually get to the target pretty fast, taking the average time of 2697. As shown on the histogram, extreme cases where the rover needs time of 20K to reach the target are occasional. At this stage we cannot say much more about his average time, because we cannot compare it to anything, but we'll get back to this topic when we introduce new search algorithms in future episodes. Let's check, however, if Ralph loses efficiency if we put him in a bigger environment, here on map of size 25. Here, the environment is bigger, hence the risk of prolonged search is greatly increased. Now, let's increase the size a bit more, let's say to n equal 50. In that situation, finding goal seems to take ages, but let's not forget that the naive algorithm was built to guarantee success, no matter the costs. If we now compare distributions of time efficiency for 1K simulations per each map, we conclude that in spite of different average times, the distributions remain more or less the same. So, let's see if increasing the number of simulations to 10K per map will translate into shorter average times needed to find the ore. As we can see in the table, increasing the number of simulations does not improve time efficiency for more than 5%. The random search approach is not the most effective way to solve the challenge and presents a variety of issues closely related to the naivety of the algorithm. But that is a great opportunity for us to learn, so let's think about the biggest areas for improvement here. One of the first things worth pointing out is that Ralph scans the same fields multiple times, which significantly affects his time efficiency. To address that, we may give him a small improvement in the form of a check. If all hexes in surrounding area have already been scanned, he will skip scanning and keep searching. The second issue we can tackle is making the algorithm more efficient. As a rule, Rover recharges regularly, but chooses the unfortunate moment. His energy never drops below 13%. Fixing the algorithm may allow to fit 2 scans before recharging. We can also add a rule that will make him recharge only when his energy drops to 0. Lastly, Ralph loses lots of his time to scan map edges. Scanning area that is behind map's edges do not give us any more information. From our perspective, Mars is a flat planet. Do not confuse it with flat Earth, where we could send Ralph one day. If we make him stay back 2 fields from the edges, he would avoid scanning the empty spaces. In future episodes, we'll take a closer look at some other approaches for searching through map, like circle search and cascade search. Feel free to share your ideas in the comments section below. What other improvements do you see that can make random search approach more robust? Can you think of any future challenges for Ralph? Thanks for watching. If you enjoyed this episode, give it a like and subscribe if you want to see more content like that. See you next time.